So I'm giving, I would say, another of the talks where I try to give a wider perspective. So instead of discussing purely technical things, I'm thinking also in harmonic analysis, we're at a time where we should go from individual components, be it, I don't know, individual groups, special spaces or so, to a more systematic, coherent way. So to see how things are connected. And I was actually almost surprised when I looked back. My first talk using the word conceptual harmonic analysis was given already about 14 years ago. And still I have so many open things and find that I have to do so many things that the intuition about harmonic analysis as a field where everything more or less has been done. This was told to us when Dieudonné was visiting us. Abstract harmonic analysis is off-stream, he said, until now, where we have time frequency analysis, function spaces, numerical things, and so many open things, and so many things that have to be done, so that I would like to share it with you. Now, at the end, after different versions of the abstract, I decided to emphasize the role of what I call BUPUs. You will see some of them here, the bounded uniform partitions of unity, and I would like to explain to you what kind of universal tool they are and how to use them. So the idea of conceptual harmonic analysis is essentially the idea to integrate the different branches of harmonic analysis, most of all abstract harmonic analysis and computational harmonic analysis. I would say abstract harmonic analysis emphasizes the analogies between different groups and says whenever you have a group, you have a dual group, the functions are living on the group, so they're Fourier transform on the dual groups, convolution goes to multiplication and so on. But many of the tools that we use nowadays are coming from time frequency analysis. So from the attempt to understand Gabor expansions, or we had to learn how to deal with slightly redundant systems, which however still stable. So we are in the context of Banach frames. I like to work with amalgam spaces and found them extremely useful. First, in order to define modulation spaces, but then they turned out to be the right spaces for time frequency analysis. And one of the favorite objects, which I think has still some potential, is what I call the Banach-Gelfand triple, consisting of the Siegel algebra is 0 and the dual space, which is meanwhile baptized the name of mild distributions, but this is just names for now. Okay, so today, as I said, I would like to concentrate on the partition unity. I don't know why I have this yellow object. Do you see it also? I think it's not too disturbing, but I don't know how to get it.
Yes, it is still visible.
You see it?
Ja.
Okay, I don't know how to erase it, sorry.
Du kannst Steuerung Z versuchen.
Yeah. No. Yeah. It's a part of the screen apparently, but I think it's not so bad. Now, the point of view of abstract harmonic analysis is to have functions or distributions living on different locally compact groups, and as I said, they are living each of them on different groups, and it's very hard to compare things except by analogy. For the engineers, the idea is to work with continuous and discrete signals, with periodic and non-periodic signals, and of course the periodic discrete signals are just the finite signals, which are discussed by the discrete Fourier transform and implemented by the fast Fourier transform. Physicists often work with vague expansions in terms of Dirac deltas. They would say they form a continuous basis, or the Fourier basis consisting of the pure frequencies. And they would say that the Fourier transform is an integral transform, which is considered a change of basis. Now, if you take the usual expressions for a basis, it's very hard, and even more difficult it would be to think that it's a continuous orthonormal basis, because that would require delta 0 to be paired with delta 0, and we know that there is trouble going on here. but in other ways, it's a very reasonable way to describe a function. Now, I would like to show you, or the plan of conceptual harmonic analysis as such is to describe all these things so that engineers have a solid mathematical background. Physicists can use these notations without sloppy argumentation. And I was told by Hans Reiter, my advisor, we should not do things by doing it for the real line and then for Rn and so on, but we should try to take each of them as a generic locally compact abelian group. So kind of what can we do, or can we do all this without structure theory? And of course, I was suggesting this because I think I can show you how to do it. Now, if we look into the literature and see what we find here, then starting, for example, many of the books, and the writer's book is an example, you would say first you have to define the L1 space, you have to define convolution, which requires integrability. It looks at least very plausible. You define the Fourier transform, which as an integral transform also requires integrability. So L1 is obviously, according to the traditional viewpoint, the natural starting point for harmonic analysis. We have convolution, and it's turning into pointwise multiplication. Whereas engineers, they would say we need to understand time invariant systems, so linear operators which map input functions into output functions. And the key argument is that they say every function is written as a superposition of Dirac. So they would say, take this spirit of continuous basis or so and call it the sifting property of the Dirac delta. So they don't explain what it is, but they use such a formula. And for me, it's more or less two ways of seeing it. A function is well defined if you know all the values. That's a triviality for a mathematician. Or you say f convolved with Dirac delta is f shifted by 0, and that's the identity operator. And that's quite true and in a way not surprising. And but how can you derive non-trivial things from a trivial statement? So now, on the other hand, when you go to the digital world, you see that the FFT is used. But what is the connection now between Lebesgue integration, the use of discrete Fourier transform, this sifting property or so? So I found it quite confusing, and I tried to read engineering papers and course material and so on. So again, if I summarize it, mathematicians use Lebesgue integration. They found that to widen their perspective, they have to use the temper distributions, or they start with the nuclear Fréchet space called the Schwartz space and take the dual. So you have to learn Lebesgue integration theory, topological vector spaces and all that, and at least Hilbert space theory in order to formulate the Plancherel theorem. I put just a few references, just writer's book, of course. I find the book of Gianfranco Cariolora on unified signal theory quite interesting, because he refers to Loomis and the abstract theory, but from the point of view of an engineer who wants to make this distinction of signals. And a little bit of the talk today will be based on the paper which I tried to finish yesterday, more or less. So this is the last reference. Of course, the natural domain of Fourier transform, to view the natural domain, the locally compact abelian groups, goes back to André Weil, and he was, of course, inspiring Hans Reiter. Now, if you look at this whole conceptual harmonic analysis framework or so, I realized over the years that there are many different branches. The first one, which I spent quite some time in the last few years, is to make it accessible to the engineers. So somehow it's a modest, if you want to say so, modest distribution theory. That's why I called the elements of S0 prime mild distributions. And I tried to teach this at Technical University Munich and ETH and so on. And I think people understood quite well that, for example, my voice is a signal. You would not think that it's important to know it pointwise almost everywhere. It's very unlikely that it's an L2 function, because I could continue forever. Don't worry. But we can record it. I can show you a spectrogram and it will be a bounded function. So somehow that's my simple definition of a zero prime. It's the collection of all the signals which have a bounded spectrogram. Now, of course, mathematically you have to define it, but you can say it's just a completion in the appropriate way. And if you think of the Light-Hill approach to temper distribution, you can say, well, a temper distribution is an equivalence class of Cauchy sequence in a certain way. And you need a lot of topological theory to justify that this view on the temper distributions is the same as the one by Schwarz with duality. That's actually something much easier in the Banach space setting with S0 and S0 prime. I just want to mention this because in the notes of these course notes, and I will try to continue them, I was really trying to say, well, let's start with easy things like the Gauss function has a Fourier transform, which is the Gauss function, basic rules, and then establish this framework, so an extended Fourier transform in the setting of S0 prime. But as I mentioned at the beginning, I would like to do all this not only for Rn, where we know many things, and where we also have dilation, so we can produce fine partitions of unity by taking any one of them and compress them. So how can we do it? And that was kind of one of the things that I wanted to show. So that's another summary. I can skip this. Yeah, maybe I should say there is one more aspect, that when you do numerical harmonic analysis or computational harmonic analysis, most of the people working in this area try to work efficiently. So speed up and give an algorithm, have a fast way to compute certain things. Maybe iterative algorithms should have a good rate of convergence and such things. But what is much less investigated is when you make a transition from discrete to continuous, you always expect that kind of the FFT is just a discrete version of the Fourier transform. So the naive approach would be, you're giving me a Schwarz function, I should compute, want to be interested in the behavior of its Fourier transform, and I will sample it. And if I do it correctly, I can sample it, take the FFT, put it back to the continuous domain by plotting it, so to say, so by piecewise linear interpolation or so. And then I would like to know, is this something which is close to the true Fourier transform defined by the integral? And the answer is, again, because I will not discuss it in detail, yes, this would be okay for S0. So the space S0 is also useful in this way. Now, another observation which was kind of even a surprise to myself was that I can create an approach where it's not at the beginning that you first start creating the Haar measure, because you need it in order to define L1, and you need L1 in order to define the convolution and the Fourier transform and all the rest. But I can go a very long way without using the Haar measure. So generically, I'm starting from a given group and I create a lot of structure relevant for harmonic analysis, kind of just like that, using a little bit or certain amount of functional analysis. Because after all, we're talking about function spaces, which in the standard way are function spaces on RD. There is so much freedom that it's not finite dimensional, meaning we are working with infinite dimensional spaces, and therefore it's clear that we have to work with functional analytic methods, because we will have not only finite sums but infinite sums. What does it mean? They have to converge and so on. Now, this is just a quick summary, and I will not go through all these points. That's kind of more for if you want to read the PDF later on, of all the things where I realized that I need or can use the BUPUs, or I think in most of the places I really need these BUPUs. The first one I will do a little bit more carefully is how to define the convolution of bounded measures, how to extend or define a Fourier transform for bounded measures, and so on, how to define amalgam spaces. I will not talk about Corbett theory or irregular sampling problems. So probably most of you know some of the areas I have been working, and BUPUs and corresponding spaces have always been useful, and convolution relations. So after all these words, let me try to show you some pictures. So I was actually taking in my MATLAB routine some easy partition of unity, maybe some bump function or so, which add up to 1. And then I was taking partial sums. So I was originally having a fine partition of unity and creating these more plateau-like functions by taking either 3 or 4 of them. So these are good examples of partitions of unity. You could say that if you would take a completely irregular set, then the partition of unity, which is still okay, I call it an irregular bounded uniform partition of unity, the definition will come in a second, that it can look like this. So what was the procedure done here? I was just adding up shifted Gauss functions, and the sum of these Gauss functions is non-zero, so I was dividing through these things. So what are the effects that you see? Well, in this area where there's a lot of gap, you're almost having a plateau function. In this area around 250 to 300, you see a lot of contributions. So they are more or less like many copies of one function. So it's just, they look still like Gaussians, but with small amplitudes. But, and that's the important thing now, in this situation, each of those functions, it's not Gauss, it was an approximation of a Gauss with compact support. So in each of those cases, the size of the support is finite. I mean, has a given diameter. The overlap of the neighbors, maybe the highest overlap is here, but if you continue, it will never get worse than here, let's say, or of course here I'm talking about the periodic case or so. And the summation of all these contributions, of course, is made to be 1. Now, there are the nice and easy guys, which are the B-splines of order 0, 1, or order 1, 2, 3, 4, or degree 0, 1, and 2, and 3. So degree 1 means piecewise linear. That's just the convolution square of an indicator function. So you have a collection of triangular function equidistantly adding up to constant 1. Or if you take the convolution square of those triangles, you get cubic splines. You see they're more overlapping. Their maximal amplitude is not 1, whereas here you have exactly the value 1 at the peak of the triangle or so. And if you would take degree 0 or order 1, you would just see a collection of step function, more or less those things that you would use in order to create a histogram. So you would say, I'm creating a histogram by applying a measure to a system of splines of degree 0, and that's excluded in my considerations, because if I'm on a locally compact group, I don't want to work with non-continuous functions, and use measurability. Anything like that is excluded. Now to the more formal definition, a bounded uniform partition of unity, abbreviated as BUPU, is a bounded family which may not only be bounded in the pointwise sense, but also in some algebra. For me, the Fourier algebra will be the key example, but you can think of 3 times differentiability and something like this. And it's a regular bounded uniform partition if you have a group, a lattice, such that the shifted versions of these things add up to 1. Now, this definition can be given for abelian groups, but in RD, a lattice is just a distorted version of the standard lattice. But you can give a similar definition on non-abelian groups, and then it's the left translation, or if you need it, the right translation or so. Now, at some point, actually, when I was introducing the Wiener type spaces in 1980, I was thinking that I should have a little bit more flexibility. And if you think of the irregular BUPU that I was showing you before, it's more like this. So it's still a bounded family in some algebra. Again, If it's just non-negative, for example, you would just say, well, these are all functions with values between 0 and 1 because they add up to 1, and that would be trivial. The uniformity is with reference to the size of this diameter. So they're living in balls of radius delta. And if this is true for all these components, we say that the partition of unity psi, or the size of psi, is less than delta. We call xi the center. And the important thing, all important thing, is that that would not be good enough for the rest, but the neighborhood relationship is given. So at each point you look at either these enveloping things, or in extreme case just the support itself, and you're saying, well, if you're giving me any fixed element in the family, and you're looking at the supports of all the other people or neighbors, then the number of neighbors, this should be an empty set, is uniformly bounded in some way. So maybe you have distances to the neighbors which are uniformly bounded by below. So you have a separated set, and it's clear that you have this condition. Or maybe you have a finite union of such uniformly separated things. And that's what we call well-spread set. These sets play a big role in irregular sampling theory, and that's essentially what we have here. Now, of course, the translation is, maybe I should mention, there's also a notion, I think it will come later more explicitly, of a UPU, a uniform partition of unity, where you just require that this is something like this is true, but without requiring that this is a discrete subgroup. And it's a paper from 91 by Leptin and Müller. They have shown that on any locally compact group, even non-abelian, you can create such a UPU. And people in wavelet theory would know that it can be done, such a thing, without having a lattice, but still a discrete set which has something like a fundamental domain. And if you smooth it out, you get such a partition of unity. So again, for our applications, this is a nice case, but we can have more general situations like this. Now, let me jump to the approach with convolution. So you're giving me a locally compact abelian group. We have translation, and we create C0s, the bounded continuous function vanishing at infinity, which contain the compactly supported functions as a dense subspace or even dense ideal. Because they are nice Banach space or even Banach algebra with pointwise multiplication, we naturally look at the dual space, and we just call the elements bounded measures, which is of course justified by the Riesz representation theorem. But for us, we should not use measure theory, but we should use the properties of a functional. Now, it's a relatively easy task to show that if you're defining a convolution between a functional and a function in this setting, by taking the flipped version of f, then shifting it by x, and then applying the measure, that you get an operator which is starting from C0 and defining a bounded function, which is also which is an operator which is commuting with translation. So the property of being uniformly continuous of the input function f goes over to the property of the output function. So it maps C0 function into uniformly continuous functions. And if you choose, of course, a Dirac measure, you will get a translation operator. But it's not completely obvious that you're getting a function decaying at infinity. So how do you get the decay at infinity? And that's the first use of this property. Okay, I think I have to jump here. Yeah, here it's again, yeah. I want to have two things. No, yeah, that's not so good. Yeah, maybe I'm first explaining this slide here. You have to use to show that for any given partition of unity with this non-negative, let's say, you can multiply the measures with these functions from the partition of unity. So the mu psi applied to f is just mu applied to psi f. That's just a joint action of the pointwise multiplication. So the mu psi are well defined. It's very easy to show that this sum defines the measure, so the sum of the pieces, that you can control the left-hand side by the right-hand side. But what is a nice and interesting challenge, but you can do it, is to show that you have exactly this identity, independent of the BUPU. So you're finding some function fi, maximizing the action of this part here, and then you have to glue together all these pieces in order to find out that this is really true. For me, this is really the analog of the sigma additivity that you have in measure theory. And so in this way, you can show that due to the properties of C0 by duality, you get this property of the bounded measures. And so every measure can be decomposed in pieces which are well localized, and this sum is absolutely convergent. In this way also, you can show that if you apply all these pieces to a bounded continuous function like a pure frequency, then the sum is well defined. So you're extending the action, which is a priori on C0, to all of the bounded continuous functions, and it's still, the extension has the same norm. So this is due to this here. Now I'm jumping back, and I'm sorry for this. What I'm showing you next is two operators which I associate with each such partition of unity. One is the spline quasi-interpolation operator, and the other is the discretization operator. The first thing would be just think of you're giving me a function by providing lattice sampling at the lattice points of a regular lattice, and then you would say if I take the triangular partition of unity, I'm doing piecewise linear interpolation of the data at the lattice points. Now we know that, or we see quickly that this is a non-expansive operator. The maximum of the spline interpolation is not bigger than the original one. And therefore also the dual operator, which turns out, if you do it correctly, is of this form, is also non-expansive. And what is it doing? It's saying, well, we collect all the information that we have at the area psi I, and we put a Dirac at this place. Now, if you would take the B-spline basis of degree 0, so the bins, you would say I'm looking at the bars of the histogram, and instead of displaying it by bars, I would say you put deltas at the height of the bars, and that's exactly what we do. So we're doing a kind of smeared histogram of the given measure. I think it's more intuitive to show you the picture here. If you take the red sampling points and you do this quasi-interpolation, actually an interpolation, you would get a step function in red. You would get the green piecewise linear interpolation for triangular. And you see here for higher order, you will get something which is more smooth, but not exactly interpolating. That's why we call it quasi-interpolating. On the other hand, if you would give me a distribution or a mass distribution here, think of the right-hand side as a continuous mass distribution. You take the triangular partition of unity, and then you compute the scalar product or the contribution of the mass to these points. You would see here it's very positive, here it's very negative. You would get jump functions. Now, how can you compare this function or continuous probability density with a discrete measure? Well, you cannot do it really, but what you can do if you have measures, you think of probability measures, you can take the distribution function, so the integral from -infinity to variable x. And if you do it for this function, which I've chosen to have mean value 0, then I would get the continuous curve, and this discrete measure would have this collection of step function. You see at every point where you have a Dirac delta here, you have a jump of the corresponding height. So here is the biggest jump upwards, which corresponds to the peak here. And you see that you would say, oh, he's just taking a step function approximation of the distribution function. I think that's the reason why it's called weak or weak star convergence. We are living in the dual space, and it's weak weaker than ordinary convergence and so on. Now, the thing that one can do in order to introduce convolution is we can check now that by this discrete approximation, we can show that every convolution operator, which is first given by this action, can be approximated by the convolution with a discretized version of it. And we can transfer all the good properties of these discretized convolutions to the limit. And so we get the following theorem. First, all the operators from C0 to C0, and engineers would call them BUPUs system, bounded input, bounded output system, with the property that if you are having compactly supported input, you have concentration. So after a sufficient long interval of watching the output, you have 99% of the scene, 99% of the output, which I think is a realistic assumption in real life. And then all of them are convolution operators. And on the other hand, if you're asking me, how can I represent my T and by what is the measure creating this, I have to say, well, feed your function f flipped into your system, pass it through the system and evaluate it at 0. So roughly speaking, it says every such operator is a moving average. But in order to have our convention that Dirac delta at x corresponds to shift by x, then you have to do this flipping stuff also. Now, due to this property that I mentioned already of extension, it's quite easy to show that we have a Fourier transform, first of all, well-defined, a bounded continuous function, and we have the convolution theorem. But we also have another quite important thing that we can approximate all these things by the discrete measures. Now, I'm taking a break in my thoughts now by saying that this was kind of something I will pursue also, but I also wanted to use other things, and for example, that if you take measures which approximate, which are Dirac sequence, then we would expect that you're having something which is also convergent to the identity operator. So of course you have it inside of L1 if you do integration theory or so. But if you're doing groups, you have to work a little bit further and you need fine partitions of unity. And so I realized, and if somebody has a hint, maybe you find something in the literature, but I was not aware of any construction of arbitrary fine BUPUs on general locally compact groups. So this was one of the things that I was analyzing. I think it was a couple of years ago for a course that I did a sketch, but now I have looked at this. So the statement, the new statement, I think new statement is the following. We can construct this, and the point is you don't need harm measure, and you just need more or less the definition and the basic properties of topological locally compact groups. So because it's non-abelian, I was writing here the group operation multiplicatively. So all these things, the support is given some small, relatively compact neighborhood of the identity, and all these supports are of the same size. And have this, they also have this overlapping property. So in certain groups, even locally compact abelian groups, you maybe run into problem if you try to have a lattice, and it's not always possible. Now, what is the consequence of having such a thing? So you're doing the whole construction, but you're also having discrete measures now. And these discrete measures are, first of all uniformly bounded. So it's a sequence, or actually a net, because you're not having a natural I mean, you have an orientation, but you don't have a natural strict order. And then the observation is that these discrete versions of the measures are weak star convergent to the measure. And if you look a little bit more carefully, it's very much in the spirit, as you say, Riemannian sums, which are also discrete measures applied with the delta at the point xi sitting in the midpoint of the partition that you assign to a given interval ab. And when you apply this to a given function f, which is continuous, here it's now in C0, then you will see convergence. So that's quite in the spirit of I would say, a Riemann integral in this set. You also have a property which is called tightness. So there is uniform concentration. These discretization don't contribute very much outside of a finite or compact subset. Now, the interesting thing is, so we have now an action of the dual space on C0, and we can define a multiplication due to this identification with the operators. So operators commuting with translation are a Banach algebra, because the composition of two such operators is again of the same form. And therefore, you can transfer by this isometric isomorphism the multiplication of operators to the multiplication of measures. But now I would like to just say, well, if you're coming now along with any what I call abstract homogeneous Banach spaces, so you're giving me any Banach space on which the group is also represented by as a family of operators. So that means we know we call rho of x this representation, and we expect that if we would try to define an action of measures, then delta x through rho should act on f by this representation. We assume that it's isometric and strongly continuous. So if you fix f, it depends, rho xf depends continuously of f. And then the claim is we can have a representation of the Banach algebra of bounded measures, which is in Banach algebra with respect to the convolution as explained just now. And everything will be fine, and will turn this Banach space into a module over M. So somehow the bounded measures with multiplication are universally embeddable in all these invariant function spaces. Now, for me, it was, or you would say it's interesting to take this for Siegel algebras, where you by definition have isometric translation. You're sitting inside L1 and you're having continuous translation. But you don't have to stay inside of L1, and then it's the notion of homogeneous Banach spaces in the sense of Katz-Nelson or so. So the examples are quite large. Many examples appear. And if the representation is just translations on the locally compact groups, then you would just say that you're getting bounded measures. And what I think is quite interesting for applications, that if you discretize those measures, so if you approximate the f, in this case of ordinary convolution, by finite translations, then you see convergence in the norm. So somehow fixing the f, the weak star convergence of the discrete measures, brackets plus the tightness, are good enough to create norm convergence. Actually, you can replace the collection of discrete versions of one measure by any discrete, by any sequence of bounded measures which is bounded, tight, and weak star continuous. And there are many examples. For example, you could say, I'm taking a nasty measure and I convolve it with a Dirac sequence. Then you would see nice functions approximating the abstract measure, and that same principle would apply. So you see here, this is the main statement. If you are having such a homogeneous Banach space with respect to the action of G, and you have a tight net which is weak star convergence, then this is turned into norm convergence. This is more or less the same in an abstract version. And when you go for a proof, you really have to only show that the discrete approximations that we have created with the help of the BUPUs, they will create a Cauchy sequence. Well, that would not be maybe a Cauchy sequence, but a Cauchy net. And therefore, it's good to check, and that's in the appendix of this fresh paper, that a norm space is a Banach space, so it's complete by definition if every Cauchy sequence is convergent. But of course, equivalently, that's how it's often proved, by showing that every absolutely convergent series is norm convergent. Or also this more disorganized, if you want, so Cauchy net is convergent. And the trick is very easy. If you take a sequence of epsilon going to 0, you can thin out your Cauchy net. You create a telescopic sum, which by point number 2 will have a limit. you see that in this way a sequence has a limit which is sitting inside the Cauchy net, and then you're showing that the Cauchy net itself is convergent. There's a warning. This is not a subnet because the notion of a subnet is more delicate, but I don't want to go into this. So again, mentioned the paper by Leptin and Müller on the existence of this one function shifted along a well-spread set. The original definition of the convolution with a characterization of systems was done in this paper from 2017. Yeah, here is the definition of the UBUs, but I can leave it out here. Now, what else can be used to do these BUPUs? The first thing is, of course, you can define amalgam spaces. So more or less you cut a given function into pieces, measure the local pieces with the local norm, and you're creating a global decay condition. If you do this, you expect that the construction should not depend on the particular choice of the BUPU, and that's quite okay. If you just think of these regular ones, which are fine, then you have to think that maybe I have to take the joint refinement, which means somebody is giving you a regular BUPU and a second regular BUPU, and you're taking all the pointwise products. Many of them will be zero, but then you will see that you're running automatically in something like the general concept of a BUPU. You can never say there is a one single function creating the joint refinement. So in that sense, it's also a justification for this. Once we have Wiener amalgam spaces, it is meaningful to define, once you have a Fourier transform, the modulation spaces by saying they are Wiener amalgam spaces on the Fourier transform side. And in this way, of course, we can create what is called Venus algebra, which was one of the motivating examples. It's a single algebra and an amalgam space with local C0, global L1. So roughly speaking, the absolutely Riemann integrable functions. Or, and that was the original way to introduce a zero, you take the space which is locally the Fourier algebra global L1. So you can imagine in this course, either on RD for the engineers or on locally compact abelian groups, I would like to introduce now a zero in order to start the business with this Banach-Gelfand triple, which is a zero embedded into a zero prime. And maybe if you need it in the middle, you can create the Hilbert space. So, well, let's recall first, how can we do it, or how is it done on RD? You take such a partition of unity and you're saying, well, whereas in the bounded measures, every function, every measure is a superposition of the pieces, in C0, clearly this is not the case. So if you cut a C0 function, the good ones are in the Wiener algebra and you have absolutely convergent sums. In the Fourier algebra, the good ones are in the space that I have called as zero. And with this characterization, you have to work a little bit to prove that the Fourier transform, well, this can be defined on any group, and the Fourier transform is moving this S0 to the S0 on the dual group. Now, of course, this is using standard harmonic analysis, but you can define the Fourier Stiltes transform of bounded measures. That's what we have already seen. And therefore, you can define the amalgam space, which is locally the Fourier Stiltes algebra and global L1. This is now done only using partitions of unity and the properties of the Fourier Stiltes transform, which we have and which we have introduced without L1. And therefore, you have to modify your your proofs a little bit, but one can prove that also this space has such a property or so. Now, there are many good properties, why I don't have to list all of them. The main point is now we can extend the Fourier transform because the test space is invariant under the Fourier transform. Let's say we are in RD first. We can extend it to S0 prime. So we have to see that every ordinary function via Riemann integral, or now we need then a Lebesgue integral, if we can, the harm measure, we can embed it, the test functions, into the dual space. So this is something that you cannot do with C0 and the bounded measures. You could already do it with the Wien algebra. The Wien algebra can be embedded into the dual space, which is the space of translation bounded measures, but that's not Fourier invariant. So that's the big advantage of this space. It's both this test space is embedded into the dual space and it's Fourier invariant. And in this setting, once you have the general Fourier transform, you can do many things which engineers would like to do. For example, verify Poisson's formula for general lattices. So the Dirac comp on the lattice has a Fourier transform in this extended sense, and it's just the Dirac comp of the orthogonal lattice. This can, of course, be used to show that sampling of a function corresponds to periodization of the Fourier transform, or periodization of the function corresponds to sampling on the Fourier transform side. You can have a very natural and easy explanation of what the spectrum, it's the complement of the co-spectrum of some closed ideal of one, what the spectrum of an L infinity function is. It's just the support of the Fourier transform of a function. So you give me an L infinity function, it's inside of a 0 prime. It has a Fourier transform, which is a distribution. Every distribution has a support, so just take that. From that, you can get all the properties of chapter 7 of Hans Reiter's book, for example. Now, in this setting, and the universality of this space is something that I have explored for a long time. You can prove what engineers need, so that was one of the focus points of the course at ETH, of course. You show that every operator now from this small space S0 to S0 prime, and as mathematician you would say, well, I have an operator from LP to LQ, but I would say restrict it to S0 and continue it to S0 prime. It has a representation as a moving average now with a kernel in S0 prime, a mild distribution, and the input is allowed to be in this space S0, but then once it's bounded operator, you can extend it. You don't worry about the existence of integrals almost everywhere, but you care about the fact that this impulse response sigma that creates the convolution operator has a Fourier transform. And therefore, the description of the operator on the Fourier transform side is just by multiplication with the Fourier transform of the impulse response function. So there's a transfer function, which is exactly the Fourier transform of the impulse response. Now, the mathematical theory existing so far was you can show that there's a quasi-measure, but the quasi-measure is just something which is locally in a 0 prime, and that's not good enough to be able to create a Fourier transform. So quasi-measures appear in this side and this side, but they cannot be transferred to each other by Fourier transform. I leave out this comment about this, but I want to mention at least that the whole thing can be extended also to operators or so. And the key is the Kernel Theorem. So every operator which is bounded and linear, of course, from S0 to S0 prime, so between any reasonable function spaces, has a kernel, or can be represented, can be viewed as the limit of integral operators, which the limit is taken in the weak star sense of S0 prime. And in this way, you can create what I call now a unitary Banach-Gelfand triple isomorphism between the kernels, which are either in S0 prime in the general case, or in L2, or in the very nice small subspace S0. And the operators that you get are, well, L2 corresponds to Hilbert-Schmidt operators. That's known in the literature. Or you have a general operator. That's what I told you. It's just from S0 to S0 prime. Or you're having a better kernel in S0, then it creates a regularizing operator, which is mapping S0 prime back to S0, actually not only norm to norm, but also weak star to norm continuous. That's what we call the inner kernel theorem. And there's another paper with Mats Jakobsen, already for a long time a preprint, which hopefully will be treated soon. It will be out soon. Now, I thought at the very end I mention at least one little thing connecting this with what is called quantum harmonic analysis. So in quantum harmonic analysis, Werner, and in the studies with Franz Lewis and Eric Scatterland, they were describing operations which show that you have functions on phase space acting on operators. And for me, this is another example of this representation of a group. So you're talking now, the group is in the abstract setting G gross G hat, or the R2D, the phase space. And you're saying, well, if you call pi lambda the time frequency shift, first time shift and frequency shift, then you can take the tensor product of pi with pi by conjugating an operator from the left and to the right. So if you would have a projection operator on a one-dimensional space, the conjugation would be the projection operator on pi lambda of the same element. So and Gabor multipliers are actually linear combination of such projection operators. So then what you have to check is that this transition of lambda goes to pi tensor pi star of lambda is a strongly continuous isometric representation at the space of Hilbert-Schmidt operators. And I would extend it and I would say it's even on the Hilbert, on the Banach-Gelfand triple. So you reduce it to the operators which are nice, and you extend it to the other operators. And then you just apply this general machinery, and you can say, well, every bounded measure mu of two variables, or on G gross G hat, and restricting it to L1, F has such a symbol. So this is meaningful. So again, T, maybe first to take the Hilbert-Schmidt operators. Franz Lewis and his team, they were taking the trace class operators, but you can take the operators in S0 or so, and then you have this approach, and can explain with this machinery quite a few things. And I think my time is probably over. Yeah, so maybe just mentioning the key to all this is that this representation at the operator level can be used in the Kohn-Nirenberg symbol. That's another version of viewing out the operators as a translation operator. So apply an operator and then take the Kohn-Nirenberg symbol is the same as first taking the Kohn-Nirenberg symbol and then taking the shift. And that explains, of course, that essentially at the Kohn-Nirenberg level, you're doing an ordinary convolution, and therefore all the nice properties that you know from ordinary convolution work fine. Now, I may want to mention at the very end that another branch which comes out of this viewpoint is the notion of a Banach for Fourier standard space, which encapsulates all the spaces that usually people are, not all, but many of the spaces people are usually using in time frequency analysis, but more or less Fourier analysis. And so these are spaces between S0 and S0 prime, which are pointwise modules over the Fourier algebra, and which are convolution modules over L1 with respect to convolution. And as we have seen, these are two integrated actions, and how do you get them? For example, you just have a Banach space, and that's now maybe the last slide, where you have isometric representation of the time frequency shift operators. Well, this is not a representation, a projective representation, but that's not so bad. You assume that some nice space, maybe the Schwartz space, is stands inside. Then you have strong continuity, so you can integrate all this, and then you get a lot of extra properties. And if you take LP, you can take amalgam spaces, modulation spaces created from this, convolution operators, Fourier multipliers. I don't know, so many things can be done. They all have these properties, and they enjoy this double module structure, which is an interesting structure in its own way. I have here some references, and I think I should finish my presentation, and thank you for your attention. And of course,